Dr. T.V. Geeta, Professor, Department of Computer Science, College of Engineering, Guindy, Anna University. Her special interest, Artificial Intelligence and Natural Language. She has published more than 143 articles in national and international journals. She has guided around 7 PhD students. She has got Young Scientist Award from Government of Tamil Nadu in the year 2000, Chief Minister's Special Mention Award in the year 2002 and Woman of Excellence by Rotary Club in the year 2003.
Welcome to the UGC lecture series. In this lecture we are going to talk about a little more about indexing and hashing. So, we are going to discuss some more issues in indexing and then we are going to explain the concept of hashing. We are going to explain dynamic hashing in detail and we are going to discuss a little bit about bitmap indices. So, let us look at some more issues in indexing. One particular problem associated or issue associated with indexing is the variable length strings that are available as keys and variables fan out. So, how do we use the space as for splitting and not base it on the pointers, because the space criterion becomes very important. So, one method of doing this is what is called as prefix compression. So, what we do here is the key values that are actually stored in the internal nodes, if you actually want to store the complete key values, it will take a lot of space. So, instead of that you just use the prefixes of the full key. So, what you do is you have to do an analysis such that you keep enough characters to distinguish between two entries in the subtrees separated by the key value. For example, suppose you have Silas and Silberschatz, which is actually, as you know, the name of the author who wrote a database book. So, if you do this, these two can be separated by using SLIB. It is not necessary to have the rest of the letters. Of course, this type of compression works only if you have done a complete analysis of the type of keys that you are going to use. So, the keys in the leaf node can be compressed by sharing common prefixes. So, this way of using prefixes and then compressing it using common prefixes is very common when you have large key values. I mean, the characters of a key value is very large. Next, we talk about an issue called multi-key access. So, sometimes what happens, you index it only by one key value, then what happens, depending on the queries, some queries it will answer very well, but some other queries it will be very poor performance because it is sorted according to the index, which is not what the query is about. So, this is an important issue again, especially for queries that are repeated very often. So, for this you use multiple indices for certain type of queries. For example, suppose you have a query like select account number from account where branch name is equal to Perry Rich and balance is equal to 100. If you have such a many possible strategies for processing the query and what are the strategies you use on the using indices on single attributes. So, you can index using branch name to find accounts with branch name Perry Rich and then test for the balance equal to 1000. Another one, what you can do, remember the query, you have balance equal to 100 or 1000 or whatever it is, the balance value. You can use index on the balance to find the accounts with balances of 1000 and then test the branch name. So, you can either have an index based on the branch name or you can have an index based on the balance. Now, how do you decide this? You can have both also. So, how do you decide this? You decide there is also third possibility. You can use branch name to index to find pointers to all records pertaining to only the Perry Ridge branch. So, you can also use another index for the balance. So, take intersection of both the sets and then you can do the operation. So, now you must have understood a little bit about how the performance of a database is affected by the type of index that is used, and so the choice of what you want to index with, okay, that is very important. So, now depending upon what are the types of queries that your database is likely to face very often, you have to do the indices depending on that. You can have multiple indices, only problem is the space constraint. Now, another thing is what is called as covering indices. So, what you do is you add extra attributes to the index so that queries can avoid fetching the actual records, particularly useful for secondary indices. So, when you are having secondary indices, you use extra attributes to the index. Now, here the issue is when you have secondary indices, these indices are considered important. So, some of those attributes are added into the the primary index itself so that you can avoid fetching. And also you can store some extra attributes only at the leaf, you do not have to do it at the beginning itself because it is not indexed according to that. Then you have record relocation and secondary indices. Now, if a record moves, up to now we have looked at for certain type of queries how the indices can be maintained. The next issue two issues we saw. One is how to compress the storage of the keys by having keys, prefix of the keys, and how that has to be done. The second one was there we had to analyze what are the key values. In the second one we had to analyze the type of typical type of queries that are asked for of a database, and according to that you have to design the indices. The third issue is what happens when records are relocated and secondary indices issues. If the record moves, all secondary indices that store record pointers have to be updated. So, node splits in B+tree file which you have seen before, this becomes very expensive. So, what is the solution to this? The solution to this is use a primary index search key instead of record pointer in the secondary index. So, extra traversal of primary index to locate the record is required. So, that will mean higher cost for queries, but the node splits will be cheap. So, when relocation occurs, the split will be cheap. So, add record ID if primary index search key is non-unique. If it is a non-unique primary key, you have to add that. Now, here you look, it is again a compromise between two issues. One is, do you want record reallocation to take more time, or do you want query handling to be done faster? So, depending on that you have to decide. So, that is about some issues of hashing. Now, let us go to the next very important issue associated with the storage of records in databases, which is hashing. Now, when you look at hashing, there are two types of hashing. One is called as static hashing and the other is called as dynamic hashing. First, before we go into whether static or dynamic, we have to decide on, we have to discuss what is meant by a hash function. So, a hash function H is a function from the set of all search key values K to the set of all the bucket addresses B. So, basically when you are going to store data, what you will have is you will have a set of buckets and you will have key values that are stored in each bucket. So, the purpose of the hash function there is given a key you apply the hash function of the key, you should know to which bucket this key belongs. So, hash function is used to locate records to access for insertion as well as for deletion. Records with different key values may be mapped to the same bucket, thus entire bucket has to be searched if you want to actually find. So, what you do is you use the hash function and you actually locate the record, but when you locate the record you may not actually locate the record, you will locate only the bucket. So, what happens, you have to search the complete bucket in order to get the actual record, locate the actual record. So, let us look at an example of hash file organization. Now, hash file organization of account file, we are using branch name as key. Now, let us assume there are 10 buckets. Okay. Now, the binary representation of the ith character is assumed to be integer I, just for simplicity. So, the hash function returns the sum of the binary representation of the characters modulo 10. So, H Perry Ridge for example will be equal to 5H Round Hill equal to 3H Brighton is equal to 3. So, how you do this is Perry Ridge, you take the characters P, E, R, R, each of those characters, and then take the binary representation of that. Ith character is assumed to be integer I. So, so you will have 26 integers basically. So, you add all those. So, P, A, B, C, D like that, P, E is 5 for example, Y is 25 for example. So, that you add all this and then you do that, and whatever number you get, that you do modulo 10, and then for that you find the hash value. There are many different ways of finding the hash value. So, we are looking at one method. Similarly, Round Hill you can have, Brighton, each of this will have different hash values. If you look at this example given here, you have a hash file organization of account file using branch name as the key. So, if you look here, you have 9 buckets 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you will look here, it is based on the branch name. So, this is the actual key that you use, these are the actual keys you use, and each of them. So, for example, Brighton and Round Hill have gone to the same bucket, Redwood has gone to the 4th bucket, Mianus has gone to the 7th bucket, and Downton, 2 values of Downton has gone to the 8th bucket. Now, suppose you get a branch name, then that branch name has to be hashed, hash function, you have to apply the hash function of that branch value, get the where it should go, which bucket it should go to that bucket, and then search in the bucket to find the actual value. You can have serials, for example, Perry Ridge has got 3, so you have to search from the beginning. Here you have to search like this, so you have to search within the bucket to find the actual record. Now, the choice of the hash function is very important. it depends on a lot of factors. There are some heuristic functions available, but the worst hash function will, what will it do? It will map all the search key values to the same bucket. That means it is equivalent to not having the bucket at all, and so this makes the number the access time proportional to the number of search key values, while in the when you use hash function, the search key value will be less than the number of it will be less than the number of search key values. And an ideal hash function is one in which the suppose you have 100 key values and you have 10 buckets. Ideal hash function should hash in such a way that it is equally distributed, that is 110 for 100 values, 10 buckets, 10 will go into each of the buckets. This is not sometimes possible. So, the average it should be distributed evenly as far as possible. An ideal hash function is uniform, that is each bucket is assigned the same number of search key values from the set of all possible values. This is what I was trying to tell you. An ideal hash function always is random. So, that bucket will have the same number of records assigned to it irrespective of the actual distribution of search key values in the file. So, whatever the search key values in the file, that without looking at that, it should actually distribute it uniformly. So, it is a random hash function, you are not taking actual values and trying to find a hash function. Typical hash functions perform computation on the internal binary representation of the search key. So, it does not do it on the actual characters, it does it on the binary representation. For example, for a string search key, the binary representation of all the characters in the string could be added and the sum modulo the number of buckets could be returned. So, the modulo you do for a hash function is equal to the number of buckets that you use. So, it is normally equal to x modulo n, where n is the number of buckets. Now, how do you get this x? No, one way of getting this x is take the binary representation of all the characters, add it, and whatever value you get modulo 10, that will give you the which bucket it should go to. For example, suppose for one particular string value we get the, when you add all the binary representations you get a value of 56, then you do 56 modulo 10. So, that will give you a value of 6. So, it should go to the 6th bucket. If it is 50, it will give you a modulo 0, the answer will be 0. So, it will go to the 0th bucket. Like this we do. Next is the handling of bucket overflows. Now, we assume that you have put it in buckets and ideally you have enough number of records that can be stored in a bucket, but that is not always true. Some bucket overflow will happen. So, bucket overflow can happen in many cases. Some of the cases are in insufficient buckets, skew in distribution of records. Suppose you have 10 buckets, most of the records go into 2 or 3 buckets and the rest have 1 1 1, that is the skew. The worst skew is it all goes into one bucket. This can occur due to 2 reasons. Multiple records have same search key value, that can also happen, and chosen hash function produces non-uniform distribution of key values. Although the probability of bucket overflow can be reduced, it cannot completely be eliminated because so for that reason we have to talk about how to handle bucket overflows. There are many methods in which bucket overflows are handled. One of it is overflow chaining. The overflow buckets of a given bucket are chained together in a linked list. So, you have this and then you have extra buckets there which are changed. Scheme where you use extra buckets which is linked to the bucket is called closed hashing. An alternative which is called as open hashing does not use overflow buckets and it is not suitable for database applications. So, let us see how bucket overflows are handled. Now, let us assume that there is a bucket 3 and there is a bucket 0, bucket 1. So, what happens here is there is these are the overflow buckets of bucket 1. Okay. So, when will this overflow bucket come? It will come when suppose bucket 1 can have only 10 values, then after if the 11th value is also hashed on to bucket 1, it will go to the next one. So, that is the way it is done, and so the hashing is the same, it will go to the next value. So, we will look at more of hashing after the break. So, now let us have a small break. Welcome back after the break. Before the break we were talking about hashing and basically how to handle hash overflows using extra buckets. Now, there we were basically talking about hashing of files. Now, hashing can be used not only for file organization, but it can also be used for index structure creation. And here what it does is it organizes the search keys with their associated record pointers into a hash file structure. But basically hash indexes are always used only for secondary indices. This is because if the file itself is, the complete file itself is organized using hashing, then it is not necessary to have a separate primary key which is organized using hash. So, that becomes unnecessarily. So, but normally the term hash index is used for both the secondary index hashing as well as the complete file organization hashing. Both are called as indexes. Let us talk about the example of a hash index. Now, you take this example here, you have here a set of records, and these are the buckets associated with each record. You have bucket 0, bucket 1, 2, 3, 4, 5 and so on. Now, if you look here, you have this is the records that are stored. This actually gives a pointer. Now, this is the secondary index, okay, hashed secondary index, and this is the actual file organization. So, now you have bucket 1 and the pointer to the actual record, bucket 2 and the pointer to the actual record and so on. So, this is the example of a hash indexed on the secondary index. Now, we were talking basically about static hashing. Up to now we were talking about static hashing. In static hashing, the function h maps search key values to a fixed set of bucket B which has some addresses. So, but however, this is not proper because the size of the file, database file by its very nature keeps growing or shrinking. So, if the initial number of buckets is small and the file grows, then there is no point in having these buckets, the performance will degrade and there will be too many overflows. So, that is you will almost be doing serial searching. So, this is not acceptable. So, another deficiency is if the space is allocated for anticipated growth, what will happen, a significant amount of space will be wasted initially and almost all the time buckets will be under full. Now, if the database shrinks again, space will be wasted. So, what is the solution to this? How to handle hashing and buckets, size of buckets, number of buckets when the database keeps changing, it either grows or shrinks. One solution is to do a periodic reorganization of the file with a new hash function. This is very expensive and disrupts normal operations. A better solution is to allow the number of buckets to be modified dynamically. So, on the fly you keep modifying or allowing the number of buckets to be modified, how many buckets you have. So, let us go to the next topic which is called as dynamic hashing. So, dynamic hashing is good for database that grows and shrinks in size. You must not use dynamic hashing all the time, you use it only for databases whose size keeps shrinking or growing very often. So, what it allows is, it allows the hash function itself to be modified dynamically. So, there are many methods of dynamic hashing. One such method is what is called as extendable hashing, which is one form of dynamic hashing. So, the hash function generates values over a large range, typically b bit integers with b equal to 32. At any time, you only use a prefix of the hash function to index into a table of bucket addresses. What we are trying to do is, we are trying to have a hash function which generates a large range, b bit integer, maybe even 32 bit integer. Then what you do is, you only a prefix of the hash function is actually used to index into the table of bucket addresses. Let us assume that the length of the prefix is I bits, where I is 0, we said the total length is 32. So, bucket address table size is equal to 2 to the power of I. So, initially I is equal to 0. So, the value of I grows and shrinks as the size of the database goes and so 2 power I. So, for example, suppose I use the prefix of 10 bits, 2 to the power of 10 will be the bucket address table. Suppose I use a prefix of say 15, then it will be 2 power 15. So, I can go from say 10 to 30 or whatever it is as the size of the database grows and shrinks. Multiple entries in the bucket address table may point to a bucket. So, how is this possible? Because the actual number of buckets is less than 2i, the number of buckets also changes dynamically due to coalescing and splitting of buckets. Let us look at an example of this. This is the complete hash function producing the data that is produced by the hash function, and this is the prefix of the hash, and this prefix will point to bucket 1, bucket 2, bucket 3, and in this structure I2 equal to I3 equal to I, where I1 is equal to I minus 1. So, this is the way you get the extendable hash structure. Now, how do you use the extendable hash structure? Each bucket j stores a value ij. All the entries that point to the same bucket have the same values on the first ij bits. So, the prefix is the same, in other words. To locate the bucket containing search key kj, you compute the hash function of kj, which is equal to x, and then use the first I high order bits of x as a displacement into the bucket address table and follow the pointer to the appropriate bucket. So, what you are trying to do is you find the hash function, take a prefix and use that prefix to find the displacement into the bucket address table and keep doing. So, when that is for accessing. Now, when you want to insert a record into with search key value of kj, follow the same procedure as lookup and locate the bucket, say j. So, you have located the bucket. If there is room in the bucket j, insert the record, that is straightforward, else the bucket must be split and insertion re-attempted. So, which we will see in the next slide. So, overflow buckets used instead, in some cases it will be overflow also. So, insertion extended table, to split a bucket j when inserting record with search key value kj, what you do is if I is greater than ii, that is more than one pointer to a bucket j, allocate a new bucket z and set I is equal to iz, which can be ii plus 1. Update the second half the bucket address table entries originally pointing to j to point to now to send. So, you have two halves. So, you have one half which was full. Now, what you do is you want to insert, then what you do, you split the original bucket into two and the lower half are shifted to the new bucket, okay, which is created now. Remove each record in bucket j and reinsert to z and recompute new bucket for kj and insert record in the bucket. Further splitting is required if the bucket still happens to be full. So, this is the way it is done. If I that is if I is greater than ij. Now, if I is equal to ij, there is only one pointer to the bucket j. If I reaches the sum limit b or too many splits have happened in this insertion, create an overflow bucket, else you increment I and double the size of the bucket in the address bucket address table, replace each entry in the table by two entries that point to the same bucket and recompute the new bucket entry. So, that reduces to the first case. Suppose you want to delete key value, locate it in the bucket and remove it. The bucket itself sometimes it can be removed if it has become empty, and if you otherwise with appropriate updates that you have to do to tell the bucket is free or the bucket is not free and so on. Deletion in extendable, sometimes you have to coalesce buckets or you have to join together two buckets, and normally you coalesce only with the buddy. The buddy you would have studied in data structure, buddy is nothing but 2 power I, that relation, buckets having the same value of ij and same ij minus 1 prefix if it is present. Decreasing the bucket address table size is also possible. Decreasing bucket address table size is expensive operation because should be done only if the number of buckets becomes much smaller than actually the size of the table. Now, use of an extended table, suppose you have this is Brighton, Downton, Beanis, Perry Ridge, Redwood, Downwell, and this is the actual hash value. Then you are going to use a hash prefix into the bucket table. Initial hash structure, bucket size is actually only 2. So, this is the way it is done. Hash table after insertion of 1 Brighton and 2 Downton. So, you have done it. So, here you have this and here you have this. Now, after this you have inserted minus, so that becomes this. Now, this is after 3 peerages happen. Now, we are assuming that peerage can, each bucket can hold only 2. So, you have an extended or overflow bucket. Now, what happens is we have added Redwood and Roundhill also. So, this is what happens. So, the buckets are you have to find the hash function, find the prefix and then do. Now, there are some benefits to extendable hashing. Hash performance does not degrade with the growth of the file because you are increasing the growth, there is only minimal space overhead. Another alternative to this whole procedure is what is called as linear hashing, but allows incremental growth of its directory equivalent to bucket address table, but at the cost of more bucket overflows. Though we saw some advantage of extendable hashing, there are some disadvantages also. Extra level of indirection to find the desired record, because you have to go into one and then from there you have to find the address and go. Bucket address table may itself become very big, larger than the memory, then in which case that itself has to be stored somewhere. Cannot allocate very large contiguous areas on disk either. So, solution is you can have a B+3 file organization to store the bucket address table. Changing size of the bucket address table is an expensive operation, though we say that it can be done, it is an expensive operation. Let us compare ordered indexing and hashing. So, ordered indexing we had covered in the last lecture and hashing we have covered here. So, let us compare this. The cost of periodic reorganization is there both for ordered indexing and hashing, but hashing is better. It depends on the relative frequency of insertions and deletions that you want to. It is desirable to optimize average access time at the expense of worst case access time. That is another compromise you have to give, and it also depends very much on the expected type of queries. Hashing is generally better at retrieving documents having a specific value of the key, while ordered queries are useful when range type of queries are asked. So, now let us go to another small topic that comes under indexes, which is called as bitmap indices. Now, bitmap indices are a special type of index designed for efficient query on multiple keys. So, records in the relation are assumed to be numbered sequentially from say 0. Given a number n, it must be easy to retrieve record n, particularly easy if the records are of fixed size. So, it is applicable on attributes that take on relatively small number of distinct values. For example, if you take gender, country, state, the number of values it can take is less, even if you can take the days of the week and so on. Income level, again income broken up into a small number of levels, then it becomes like that. For example, 0 to 999, 10,000 to 19,999 and so on. What is a bitmap? A bitmap is generally just an array of bits. In the simplest form, a bitmap index on attribute has a bitmap for each value of the attribute. So, for example, suppose you take here, it has as many bits as record. Suppose, so here if you take gender, so you can say male is 10010 and female is 01101. So, bitmap for the income level again, so you can have it bitmap like this L1, L2, L3, L4, which will indicate the range of the salary. So, this is another way, instead of storing the complete values you can. So, bitmap indices are useful for queries on multiple attributes. It is not particularly useful for single attributes, and you can use queries can be answered using bitmap operation, intersection, union or complementation. So, each operation takes 2 bitmaps of the same size and applies the operation on the corresponding bits to get the result map. So, this is possible. It is generally very small, the size is very small compared with the relation size. Deletion needs to be handled properly and should keep bitmap for all values, even the null value. So, now let us just a little bit talk about index definition in SQL. You can create an index like this and use create using the create index command, and use create unique index to indirectly specify that and enforce a condition that the search key is a candidate key. To drop an index, you just do this. So, and you can also have hash values which are partitioned in this value. So, these two together has this hash value, like this also you can do. So, in this lecture we have discussed some issues in of indexing which we had not covered in the previous lecture. We have explained some concepts of hashing, we have explained dynamic hashing, and we have explained some cases where bitmap indices will be useful. Some of the exercises given to you, please explain the concept of hashing, discuss the difference between static and dynamic hashing, and explain how bucket overflows are handled in static hashing, and explain the insertion to and the deletion from extendable hash structure, which is a special type of hash structure that has been defined. Thank you.